Okay, so let's do a run through of the topics that I'm intending to put into the energy and thermal test. Some of these topics you'll have done at school, and some of the topics will have been done online. And exactly how much of each is school and online will depend on which group you were in. Obviously, a little bit tougher on those topics that you've done at home. Right, so this is my plan. Recap GPE and KE. Mention efficiency, but we did efficiency in year 8, so that shouldn't be hard. Do a quick fly through the particle model and its evidence. Talk about pressure and gases. Talk about heat transfer, but again, heat transfer was something we did in a big way in bit of year 8. Briefly, cooling curves. Newton's law of cooling is not required on the course, but it sort of describes what's going on, which is why I mention it. Internal energy. Now, I don't know how much you've done about internal energy. It's a term the exam board use, and therefore it's a term I need to mention. Change of state, specific heat capacity and specific latent heat. You've done quite a bit on that. We've set quite a few videos and things on that, as well as videoing a couple of experiments on those. And I hope all of you will have watched those experiments and drawn the graphs, interpreted the data. And just briefly, the calculations that might come with SHC and SLH. I'm not going to do loads of calculations all the way through this because they're something that we've practiced in other videos and things that we've practiced at school. Plus, when I'm setting an online multiple choice exam, I'm not going to be setting huge numbers of calculations, though I will be setting some. Okay, let's just start off with a very quick recap of energy. You may remember first law of thermodynamics says that energy can't be created or destroyed, and so consequently we end up with talking about types of energy, because what's going on is that one type is being transformed into another type, and that transformation is called work. And so we end up with a list of types. Kinetic is the energy something has just because it's in motion. Gravitational potential is the energy that something has because of its position with respect to a large gravitating mass, usually the Earth. Magnetic and electric potentials, they're the energy something has because it's in a magnetic field or it's in an electrical field. Elastic potential, that's the energy something has just because it's been stretched or compressed. Thermal energy, we'll talk a lot about thermal energy, that's going to be the main part of this thing. Internal energy, we're going to come back to it. It's a combination of thermal energy and chemical potential. There you go, chemical potential energy. Some chemicals really want to go through chemical reactions, and in the process of going through those chemical reactions will release heat. They'll do work. They'll turn their chemical potential energy into usually into thermal energy, and the chemicals that are the end result of that reaction will have a whole lot less chemical potential energy available. It's a bit of an odd way round of looking at it, but it's sort of necessary to manage to keep the first law of thermodynamics going. Essentially what happens is the chemicals become more stable. Coal, not an especially stable combination of carbon. There are more stable combinations of carbon, like diamond. So if we set fire to coal, it will go into a much more stable chemical, carbon dioxide, and in the process release a lot of heat. Now these last ones, these days are sort of treated more as transfers than types of energy. So these are ways of moving energy around, ways of doing work perhaps, more than they are specific types. There's nothing wrong with saying sound energy or light energy or electrical energy, and you'll find me doing it. But the usual sort of the more accepted way of doing things in your GCSE is to treat those as methods of moving energy more than types of energy in and of themselves. Now, that blah blah blah, the only ones that we're really concerned about are the ones that we can put equations upon, because you can set exam questions when you've got calculations to do. So we're interested in kinetic because we have this equation for it. We're interested in gravitational potential because we have this equation for it. And of course, thermal and internal are things we're going to have equations for a bit later on. So these are the ones that are going to turn up most when we're discussing energy, because these are the ones that they can actually set calculation questions for. And of course, you know what the formulas are. That's just E for energy with a subscript telling you that the energy is kinetic energy is equal to a half mv squared. And then we have GPE, which is the mass times the gravitational field strength times the height, or it's the weight times the height, because of course mass times gravitational field strength is weight. So mgh or just weight times height, either one of them will give you the gravitational potential energy. Now, in almost all of the energies, actually what we're talking about is not the absolute energy, we're talking about the change in energy. So that's very true with gravitational potential, for example. When we're talking about gravitational potential, we're actually really talking about its change compared to something. So a book might have a specific gravitational potential energy if you were holding it up above the floor, and its gravitational potential energy is really compared to the floor. What's the change with respect to the floor? Because you might be on the 20th floor of a tower block. The floor isn't necessarily the earth. And so it's the change with respect to something. Something I say is normally floor level or table level or whatever it might be. And that's going to be true when we get onto the thermals as well. It's going to be the change in thermal energy. It's not going to be the absolute thermal energy that we're taking an interest in. And that's true for almost everything else. Perhaps the only one that we can say we sort of know the absolute value for is kinetic, because with kinetic we're considering the change with respect to it not moving. And so that must be an absolute value, because we know what zero is. Don't really know what zero is for gravitational potential energy. Is it the surface of the Earth? Is it the inside of the Earth? Where is it? Don't really know. So we use whatever's convenient. Okay. Right. I made up a silly question. It is a bit of a silly question, but on board. Designs of a maglev train on the moon. Believe it will be frictionless, and there is no air to provide air resistance because you're on the moon. So the train starts off from still by descending a slope on an 80-meter crater wall. How fast will it be travelling at the bottom? Well, you look at that, it's going to descend 80 meters. There's no friction, there's no air resistance, and you're thinking to yourself, crumbs, that's going to be going fast. But it's on the moon. And so the thing about it being on the moon is this. The gravitational field strength isn't 10, it's 1.7. So actually, it's not going to be incredibly fast, because the value for G, where we always use 10, we're actually going to use 1.7. And I've just done that because it keeps me interested. So no friction or no air resistance. Therefore, we can say that the GPE that it started with at the top is going to be equal to the Ke that he ends up at the bottom. Therefore, mgh at the top must be equal to a half mv squared at the bottom. And you're all savvy enough now to spot that I can cancel the m's from both sides. And so I get gh equals a half v squared, which I'm going to rearrange by taking the half across. What's the opposite of halving something? It's doubling it, so I always do the opposite on the other side of the equation. So I've got 2gh equals v squared. And what's the opposite of squaring? It's square rooting. So on the other side, I square root, so I get v equals the root of 2gh. But because g is only 1.7, then this isn't going to end up being massive. It's just over 5 meters per second, 12 miles an hour. So not massive. Whereas had that been 10 in there, we'd have been up closer to 80, 100 miles an hour. So gravitational field strength on the moon being a lot lower means that this kind of problem gives not quite the answer we were expecting. Now, this is a bit of a facetious question, but I would be a bit silly. Normally, if you did this kind of question, you would be told that air resistance was negligible. It'd be something falling, you'd be told air resistance was negligible. And so you do exactly the same calculation I've done with 10 in there, and you'd just be ignoring air resistance. You'd know it was there really, but you wouldn't be paying it a huge amount of attention. Right, there's also efficiency. Now, again, efficiency, we did it in year 8. It's not especially difficult, is it? Efficiency is the useful output power divided by the total input power. And you can do it in terms of power, or you can do it in terms of energy. Doesn't matter, as long as it's power on top and the bottom, or energy on top and on the bottom, it doesn't matter. Because if you think about it, in order to get from power to energy, you multiply by time, and as it will be the same time in both of them, times time there, and then times time there, as it's the same time in both of them, the time will just cancel out and not make the slightest bit of difference to the calculation. Okay, first law of thermodynamics says that number's got to be, can't exceed 1, because you can't create energy. Second law of thermodynamics says that that number's normally going to be less than 1, only for sort of quantum mechanical systems, and we're going to expect that to be 1. What second law of thermodynamics, quite complicated, but one of the simplest ways to think about second law of thermodynamics is it says that if you've got a large machine, you are going to get less useful work out of it than the total energy you put in. That's that written out as a formula instead of a word equation. I tried to do with the year 8s, but the year 8s really don't like formulas and Greek letters. That's the Greek letter eta. Because we use E for energy, so we can't use E for efficiency. So we use eta, because it's also an E, but of course it doesn't look like an E, it looks like an M with a tail. So kind of question, look, driving at a steady speed, electric cars' batteries are producing 1.2 kilowatts. What's the breakout power output of the car? Essentially, what's the brake horsepower? But we don't want the answer in horsepower, because horsepower is a silly unit. So therefore, we want the answer in watts or kilowatts. If the efficiency of the car's motors is 82%. Well, I hope you can see that that's easy. There's my equation. I want that bit presently being divided by that. And so I've got to take that to the other side of my equation. So I get the efficiency multiplied by the energy in is equal to the energy out. Now, the only little tricksy bit here is that I've told you it's 82%, and you've hopefully done enough percentages in your maths to instantly realise that 82% is the fraction 0.82, or the decimal rather, 0.82. And so I don't multiply by 82%, I multiply by 0.82. If I wanted to multiply by 82%, I'd have to do 82% divided by 100, because that's what percentage is. So I end up with just under a kilowatt as being the output power. So the batteries are making 1.2 kilowatts, but they're actually being transferred to the road. Power outputs for cars are measured at the brakes. They're measured at where the wheel is attached. Right. Now, some of you have done this. Some of you have looked at it and ignored it. Some groups won't have seen it at all. This was a set of questions and a little animation to design a roller coaster that was put together, not by us. And I've just popped this in because this is a question that combines the two things we looked at already. So it's looking at GPE being transferred into KE, but the energy, there is an inefficiency. Our roller coaster, as it goes down, is going to lose some energy. It's not my roller coaster on the moon. There is going to be air resistance, there is going to be friction, and so it's only 82% efficient. It's funny that it's 82 again. I honestly hadn't seen that number before I wrote the 82 on the previous slide. So it's only 82% efficient. And so this is combining turning GPE into KE and efficiency in one set of problems. So the question asks, calculate the GPE at the selected height? Well, the selected height is on the picture there, look, 19. So therefore we've got MGH. It tells you on a page that you can't see that the M is 5,000, and to take G as 10 as we do for our GCSE when we're on Earth, and the height is 19 as shown on the picture. So there's my GPE calculation. Gives me 950 kilojoules, or 950,000 joules. I just couldn't be bothered to write the 3 zeros, which is why I wrote it as kilojoules. And then what will the KE be when it's at the top? Well, of course, KE is nothing. It's not going anywhere. Therefore, the total mechanical energy is just going to be the GPE. Now, at the bottom of the slope, it's down at ground level. So the GPE has now dropped to 0. And it's the KE that is going to be the energy. But because of this 82%, the first thing we've got to do is we've got to work out how much of the energy that it starts with up here, it ends up with when it's down here. And so we've got to do as we did in the question before, which is multiply by 0.82. There you go. We end up with 779 kilojoules as our total energy at the bottom, because we've lost 18% as heat and sound. So that's our total energy. None of it is GPE, all of it is KE, and so that's our total KE. So we say that's equal to 1/2 mv squared, remembering that I've been using kilojoules, but I can't use kilojoules when I'm actually doing a calculation, so I need to convert that back into joules for the calculation. And we did the calculation on the page before, so I'm not going to go through all that rearrange all over again. Hopefully you can do the rearrange. And my answer is it will be going at, I think I'd probably be justified in calling that 18 meters per second, because there's only 2 significant figures in any of this data I've got over here. So I probably should just call that 18 meters per second. And 18 meters per second is, is going to be over 40 miles an hour. So that's, pretty quick by the time it's going at the bottom, even though quite a bit of energy has been lost to heat and sound. Okay, so that's the kind. Right, so that brings us sort of out of energy and into thermal, and we have this particle model. I find it interesting that the particle model was not accepted until the beginning of the 20th century. Right up to sort of the First World War and into the Second World War, there were eminent chemists who didn't believe there was such a thing as atoms. And all of this is not really established until it's Einstein who explains what Brownian motion is. And you'd thought Brownian motion would be something that didn't require the genius of Einstein, but no, it was Einstein who explained what was going on and helped to establish that atoms were a real thing. I say so. This is 1905 that he does that. You'd think this would be something that would be sorted out much earlier than that. This picture here, at energy, we go from a particle model is that everything is made up of tiny particles. Impossible for us to get our heads around how tiny. Think of the tiniest tiny you can possibly think you're imagining, and you're nowhere near tiny enough. But the issue with these kind of pictures is always the same, in that they end up drawing the liquid as if it's more spaced apart than the solid, and it's not really true. There's not much volume change when we go from a solid to a liquid. In fact, water, you might know that when a water goes from a solid to a liquid, its volume actually goes down, because the the molecules of water are more spaced out when it's solid ice than they are when they first become water. So all of these diagrams I looked for better ones when I was looking online. All of these diagrams are the same. They all show the atoms in the liquid, or the molecules in the liquid, being spaced further apart than they are in the solid, and that just is not true. And then when we go from gas, there's a dramatic change, huge change. And so the gas molecules are really widely spaced compared to the liquid molecules. And part of the huge amount of energy that we need to do to turn a liquid into a gas is that this huge volume of gas that's created by turning a liquid into a gas has to push the air out the way so that it can be created. It's got to create a space for itself to exist in. And it requires energy, and that's actually a big chunk of the energy necessary to convert a liquid into a gas. So again, this box here is probably wrong. It's showing we can see 3 molecules of gas there. Well, the chances are we probably wouldn't see 3 molecules of gas there compared to how many we'd see, one disappearing out the corner. And so this leads us to a term that sort of turns up in our GCSE, which is called incompressible. Which means that a liquid, there are no spaces. It doesn't matter what this picture shows. There are no spaces between the atoms in a liquid, and therefore a liquid cannot be compressed. Gas, there's huge spaces, and so a gas can be compressed. Now, you know that our evidence for this is Brownian motion. And I hope you've all seen what I've got pictures of here. I hope you've seen the light from a lamp going into the gas cell where it strikes the smoke particles. It then goes up the microscope, and we can therefore watch the movement of the smoke particles in the microscope, and you get an image a bit like this one over here. And you get this sort of zigzag motion for the smoke. And I think my video might even work. Oh well, video don't work. Never mind. You've got the picture. So Brownian motion. I'm saying, hopefully you've all seen this in the lab or watched a video of it if you weren't in the lab. If COVID had locked us out at the point when you were going through Brownian motion. Oh, there you go. Video's working now. There you go. There's the smoke cells.
Something like about times 40 times 50. And what you're seeing are particles of soot reflected in the light. The particles.
So the conclusions that we get from Brownian motion are that the air particles are too small to see. The much larger smoke particles are moving randomly. And when I say much larger, the smoke particles are probably thousands of atoms of carbon, whereas the air particles, of course, are going to be 2 atoms, N2, O2. So when I say much larger smoke particles, I mean much larger, thousands of carbon atoms compared to sort of 2 nitrogen atoms. Sudden changes in direction given a jerky motion are a result of the impacts from the underlying air molecules. Now, if the air molecules are having such a dramatic effect upon the large smoke molecules, then they've got to be moving extremely fast. And the random motion of the smoke implies there must be a random motion of the air molecules. And we haven't done this experiment, but if you heat the air up, then you get more violent collisions and the smoke moves around a lot more. Therefore, hotter air moves faster, which means that one of the key sort of conclusions of the particle model that the Brownian motion is evidence of is that temperature is a measure of Ke of the particles within the substance. So as temperature goes up, the particles within the substance move faster. Now, if it's a solid, that means they're oscillating in position, but they oscillate backwards and forwards faster. If it's a liquid, it means they change position faster. If it's a gas, it means they zip around faster. So temperature is a measure of the average Ke of the particles in a substance, and that's what the particle model says. And Brownian motion is our evidence for the particle model. So not properly interpreted until Einstein in 1905. Now this leads us to pressure in gases. So the pressure that a gas exerts on its container arises from the change in momentum, the rate of change in momentum. Now you ought to remember impulse. Impulse equals change in momentum, and then the rate of change of impulse gives us force. Force is equal to mv minus mu all over t. Now, because v and u are vectors, if something hits a surface and bounces back off again, even if it bounces back off with exactly the same speed, it bounces off in the opposite direction, and so we get a big change in momentum. So the rate of change in momentum therefore gives us a force, and a force divided by an area gives us a pressure. And so the pressure in a gas, the pressure on the outside of a gas, on a surface within a gas, results from the rate of change of momentum from the molecules rebounding off the surface. And you have to use that terminology if you're asked this question in the exam, or you don't get any marks. Increases in the temperature increases the molecule speed, as we were saying in the slide before. And increasing the speed of the molecules means they're going to collide with the sides more often and with a bigger momentum change because they're going faster. And you've got to say both those two things if you want the marks. Decreasing the volume that a gas is of a gas container increases the pressure because you increase the collision rate. There's a smaller volume for the molecules to cross, so you increase the collision rate. And it probably decreases the area. You're thinking, how can it only probably increase the area? Well, maybe the shape has changed. You might have done in maths that the different shapes have different surface areas for the same volume. So maybe it's the shape of the container that has changed, and therefore we've got a smaller volume for the same surface area. That's not impossible. It's unlikely, but it's not impossible. So this is the key one. There's a smaller volume for the molecules to cross, and therefore there's an increase in the collision rate. And when these kinds of questions turn up, people always talk about the gas molecules bumping into each other. No one cares. We're interested in the gas molecules bumping into the surface. We are not interested in the gas molecules bumping into each other. They probably don't even bump into each other very much because, as I've said, there's a lot of nothing in a gas. They're probably not bumping into each other very much, not until they become a liquid. So we're interested in them bouncing off the surface. We're not interested in bouncing off each other. But I tell you, everybody who writes an answer to an exam question on this stuff always ends up whittering on about the particles bouncing off each other. Now, the volume one leads us to Boyle's law, which says that pressure and volume are inversely proportional, which is P is proportional to 1 over V. But the useful version of Boyle's law is this one, and I hope you'll remember doing this, which is P1V1 equals P2V2. So you have situation number one, where you're told a pressure and a volume of a gas, and then you have situation number two, where something has changed, the volume's changed, or the pressure's changed, and you haven't been told one of these two. You've been told P, you haven't been told V, and you've got to work out the missing pressure. Well, you just multiply together the pressure and volume in the starting situation, and essentially you divide by the one you know in the second situation, and that will give you the one you don't know in the second situation. So you get P1 over V1 over V2 is equal to P2. Or it could be P2 under there and V2 up there. It wouldn't make any difference. Okay, heat transfer. Again, year 8 stuff. The net transfer is always from hot to cold. It's never the other way around. That's another consequence of the second law of thermodynamics. Radiation. Now, this is a problematic term. I'm always banging on about this, but I'm going to bang on about it again. It's a problematic term. Radiation is the word physicists use when they aren't certain what is moving the energy around, or it's not obvious what's moving the energy around. You know, if you put your hand next to a fire, your hand gets hot. It's not obvious why your hand gets hot. The answer is it's radiation from the fire. It's not convection from the fire, because your hand would have to be above the fire for it to be convection from the fire, and you're not going to be stupid enough to do that. But if when your hand's at the side of the fire, it's still getting hot. Convection doesn't go sideways, and so that's got to be radiation. So radiation is the term physicists use when energy is being beamed around, but what's doing the beaming is not obvious. So here we've got heat being radiated. When we're talking about nuclear physics, we're talking about energy being radiated from a decaying nucleus. We're talking about huge amounts of energy and it being quite dangerous. But the term radiation doesn't make it dangerous. Radiation just says energy is being moved. There was a thing a physics teacher put on Twitter recently, that he'd taken from BBC Bite Size. Oh my God, they had completely misunderstood radiation. They talked about infrared radiation being dangerous because it came from the nuclei of atoms. I mean, properly wrong. And this is BBC Bite Size, the thing you were supposed to use to help you with your revision. It was really bad. So here we're not talking about nuclear radiation. We're just talking about a bit of electromagnetic radiation. And the specific type of electromagnetic radiation we're talking about for sort of day-to-day temperatures is called thermal infrared. And you all know about thermal infrared because you've all played shoot-'em-up games where you put on an infrared sight and suddenly the sniper that was hiding from you, you can see them because they're glowing red. And that's these things actually exist. These are cameras mounted on a gun, and the camera isn't using visible light in order to see. The camera is using thermal infrared in order to see, and so it sees things that are hotter than their surroundings. And as a person is hotter than their surroundings, they see the thermal infrared coming off the person. As temperature rises, we get more and more infrared. and it moves up, and so it becomes near infrared, i.e. it becomes nearly visible, and then eventually it will become visible, and we've got the term red hot. And red hot means it's now producing so much electromagnetic radiation, it's even producing some in the visible spectrum, and so the thing that we're heating starts to glow red. And the absorption and emission is dependent upon the microscopic surface, i.e. is it matte or shiny? And for visible light only, but in an exam they don't normally worry about that, the surface colour. So black is better than white when it comes to absorption and emission of radiation. You remember all this, we did it to death in year 8. Convection. Density differences cause motion, and the motion moves the hotter molecules, and because the hotter molecules are moving, essentially the heat is moving. But don't say the heat is moving, say the molecules are moving. If you say heat goes upwards, you get no marks. If you say hot air goes upwards, carrying the heat with it, you get marks. Notice it's got to be under gravity, because it's the density differences having different weights leads to the buoyancy force or the upthrust, and therefore we've got to have some gravity because they've got to have a weight. And so flames behave in a completely different way on the International Space Station. There are some pictures there are some videos online of flames on the International Space Station, and they're quite bizarre because there's no convection going on. Right, and then finally conduction. Everybody remembers conduction. You all remember sort of one molecule knocking into the next molecule, knocking into the next molecule. Lots of people have it in their head that it's only solids that do conduction. That's not true. Everything can do conduction. Even a gas could do conduction. It's just because, as we've discussed earlier on, the gas molecules don't bump into each other very often. It's rubbish at doing it. It doesn't mean it can't do it. It just means it's rubbish at it. Whereas in a solid, because all of the molecules are all alongside each other and rigidly held together with bonds, if one starts moving, the rest are going to start moving too. We tend to talk about conduction in solids. But that one molecule bumping into another is only one of two mechanisms. The other mechanism is free electrons getting hot and diffusing. So the free electrons at one end of a bit of metal that's being heated, they get very hot and they rapidly spread throughout the metal, spreading the heat throughout the metal with them. And so that explains why metals are very effective at heat transfer. That's the question that we used to put in the year 8 exam. You've got a bicycle, two bicycles. One bicycle's got rubber grips on the handles, the other one's got bare metal. It's a cold day. You grab hold of the one with rubber grips, you're quite comfortable. You grab onto the one with the bare metal and you're uncomfortable. We'll get kids saying things like, the metal's colder. Well, it's not true. They've both been sitting in the shed waiting to be taken out for a bike ride for a long time, so they're both at exactly the same temperature. What's true is that the metal will conduct the heat of your hotter hand away very effectively. And so what you're feeling is that heat leaving your hand. That's why that's uncomfortable. Whereas the rubber, absolutely terrible at conducting the heat away from your hand. So the heat tends to stay in your hand, and so you're a whole lot more comfortable. But the temperature of the rubber and the metal are the same. Don't know what I'm blaring on about that. It's year 8. Right, heating and cooling. I just wanted to emphasise the fact that when it's time on this bottom axis, heating and cooling tend to be curves. This curve here is called Newton's law of cooling, which basically says as something gets closer and closer to the temperature it's cooling to, the rate of its cooling slows down. It's actually exponential. So an example of an exponential decay curve. You don't need to know that. You just need to bear in mind that this is going to be a curve. If I cool something down over time, it's going to curve. And you know that because you've done the experiments, or even if you've only done them virtually, of the cups of hot water cooling down, and you've seen these curves. And they curve to is it asymptotic? Something like that. The maths word for they curve approaching a straight line, and approaching it, but never quite getting there. And that's what happens with Newton's law of cooling. And then a similar kind of thing happens when we're heating stuff up. It's not quite the same process. What's going on here is as this object gets hotter and hotter and hotter, it's going to be radiating the heat away faster and faster and faster, because it's getting so much hotter than its surroundings. And so you get to it's a bit like terminal velocity. You get to a point where it doesn't matter where any extra heat you put in, any extra energy you put in, is just being radiated away or convected away, because the thing is now so hot compared to its surroundings. It's just shifting the heat out. So when you're pumping in kilowatts of energy, all you'll do a kilowatts of energy, you're doing a keeping it at the same temperature. And so you get these curves as it gets closer and closer to the temperature, its maximum that it's capable of holding, its terminal temperature. You get these curves. So if it's time on the bottom axis, when we're talking about heating and cooling, it tends to be a curve. However, we can get these flats in these curves. Again, must be time on this axis. We get these flats. And they occur when there's a change of state. We'll talk about a bit more about that in a minute. Now, internal energy. Let's just talk about that term, because our exam board have started using it, so you guys got to know it. It is the total thermal and potential energy of a substance. If we think about argon, argon's a noble gas. It doesn't really want to do any chemistry. And so the chemical potential energy of argon, largely insignificant. And so the internal energy of argon is going to be pretty much whatever its thermal energy is going to do. And in terms of chemistry, or it's very turning it into a liquid. There's not going to be dramatic changes. Whereas other things, they want to bond, and so and they want to go into nice rigid structures. They want to be solids, or they're happy as how keen something is to be a solid and stay as a solid, how keen it is to turn into a liquid. They're all represented in the potential energy of the substance. What's the bonding environment doing? So this is how much the molecules are bouncing around. This is how much the molecules are attached to each other. So I think that's just what I've just said. Blah, blah, yep. Adding heat usually raises the thermal portion. Removing heat usually lowers the thermal portion. So adding heat normally heats it up. Temperature goes up, because the temperature is a measure of the kinetic energy. Now, if the kinetic energy is going up, temperature's going up. Removing heat, taking the energy out of it, the kinetic energy, we're taking energy out of the kinetic energy bit, the molecules aren't moving as fast, temperature goes down. But when we've got a change of state, melting for example, when we've got it going from being a liquid into a solid, or a solid into a liquid, it's the potential energy portion that's changing. I should say portion, not potion, sorry about that. It's the potential energy portion which is changing. And so the temperature will stay the same, because the temperature is a measure of the kinetic energy bit. And the kinetic energy of the molecules isn't changing, it's the potential energy of the molecules that's changing, because the bonds are reorientating themselves into a solid, or the solid is breaking up and becoming a liquid, or what bonds there are within the liquid are breaking apart, and the surrounding gas is being pushed out of the way so it can turn into a vapor. And so it's the potential energy bit that's changing at that point. And so although we can be pumping in loads of heat, or pulling out loads of heat if it's in a freezer, the temperature stays the same until that process is over. And so that heat involved in that is called latent heat, because latent means a property that can't be seen. It's there, but it's not obvious it's there. So latent heat, we know there's heat being moved, but we can't see that there's been heat being moved because there's no change in temperature. But we know there is heat being moved. There's just no obvious change in temperature, so we can't see it. So we call that latent heat. And here's the typical diagram. I use this one of all the ones available to be on the web because the scale is right. The energy necessary to turn water into a vapor is enormous, much bigger than the energy necessary to turn ice into water. But these are our latent heats. So that bit there is the latent heat of vaporization of water, and that one's the latent heat of fusion, fusing into an ice. I'm not going to get vaporization on there even if I could write it. Okay, and so we get these dwells, we get them sitting at these points, staying at the same temperature until we've changed all of the potential energy from being the potential energy environment of a liquid to the potential energy environment of a gas, or the potential energy environment of a solid to the potential energy environment of a liquid. And whilst that change is going on, we don't get a temperature change. Notice these are straight lines. I said that they had to be curves. These are straight lines because this is energy. Q is often used for the energy. So this is energy on this bottom axis. It's not time anymore. So it's probably taking longer to put the heat in there. But as we're measuring the amount of energy going in, the fact it's taking longer doesn't matter. All right? So look for what's on the bottom axis. And then this word specific. Specific means per kilogram. So specific heat capacity, C. The energy needed to change the temperature of 1 kilogram by 1 degree C. Heat capacity is the energy needed to change something by 1 degree C. We haven't specified the mass. The specific heat capacity, we specify the mass, 1 kilogram. And then the specific latent heat is the energy necessary for 1 kilogram to change from solid to liquid. This is the one of fusion, so it's solid to liquid. If we do the one for vaporization, it's 1 kilogram from liquid to gas, liquid to vapor. Don't say 1 kilogram, don't get the marks. Here's the equations. In both cases, the top one is perhaps the proper equation. The bottom one is the one I tend to use. I'm not a huge fan of using Q for energy, probably because I was originally an electrical engineer and we use Q for charge. So I'm not a massive fan of Q for energy. Chemists and thermodynamicists do use Q for energy. I tend to use E for energy, or for all of my energies. I don't change to using a different symbol just because it's heat. And theta is the proper thing when we're talking about temperature, but a capital T is much easier. I know it has that risk of being confused with time, which is perhaps why we ought to use theta, but I tend to use capital T. And so we get E equals mc delta T, because delta means changing. So energy is equal to mass times specific heat capacity times change in temperature. Every group I've ever had, I've always ended up calling that MCAT. And then they remember it. I mean, it's a silly name for it. That does not say MCAT. But every group I've ever had always ends up calling that MCAT, and then they remember what they're talking about. MC delta T or MC delta theta, where you've watched videos that have done it properly and weren't sort of done by me. And then again, I've Q equals ML, where L is the latent heat. I tend to use E. The latent heats, the specific heat capacities are per kilogram, and so your masses must all be in kilograms. Right, so a quick look at the calculation. I've gone one too far, unfortunately, so I've turned up a bit I didn't want you to see. Anyway, 80 grams of ice at minus 20 degrees C is heated to 80 degrees C with a 500 watt immersion heater. Assuming all the energy is absorbed by the ice, it's probably not true, but we're going to make the assumption, none's lost to the surroundings. How long does the process take? Well, no, there's no time in there. How do I get time? Well, of course, you're going to get time because you're told power. And you know that energy is equal to power times time. So if I've got a power and I want time, then I've got to find the energy involved. or what energy is involved? Well, if, you know, you've got to sketch, always sketch. So I'm starting, let's change colour. I'm starting at -20. I'm heating my ice up. When it gets to 0, it's got to do a change of state. So it's going to sit at 0 for a while. And then I'm going to heat it up further up to +80. So I've got 3 different steps, each one of which, this is energy on this axis, each one of those steps requires energy. So to get from -20 to 80, I've got to put in the energy to heat it up to 0. I've got to turn it from a liquid in a solid into a liquid, and then I've got to heat it again up to 80. So 3 different steps. And I've got different specific heat capacities for the 2 steps. The specific heat capacity for ice is actually different to the specific heat capacity for water. So that's specific heat capacity ice, specific heat capacity water. That's what those 2 subscripts mean. Obviously, in a real question, they'd be written out more thoroughly than that. It's only because I'm doing it in shorthand. And then here we've got the latent heat of fusion. So first step is the heating up from -20 to 0. So we're going to use MCAT. 80 grams is 0.08. So many of you get that conversion wrong. You'd have called that 0.8 because you think it's 100, and because it's 1,000. So 0.08 is the mass. The specific heat capacity is 2.1 kilojoules. Well, we don't work in kilojoules, we work in joules. So I've got to multiply that by 1,000, gives me 2,100. And then the change in temperature, I've gone from -20 to 0, so the change in temperature is 20. So that's the first bit. The second bit is this, and that's E equals ml. My M hasn't changed, and L this time is 330 kilojoules, so 330,000. And then the final bit, running up here, is another MCAT, same mass. This time, however, we're using the specific capacity of water, not ice. So it's 42 kilojoules per kilogram per degree C, 4,200. And then the temperature change is going from 0 to 80. So the temperature change is 80. So 3 things, I'm going to bung all the 3 in my calculator, and that gives me that as my energy. So that's my energy. But of course, energy isn't what we've been asked for. We've been asked for time. So I've got to go back to this equation that we first talked about. Energy equals power times time, therefore time is equal to energy divided by power. That gives me that as my sum, which is, on my calculator, 113.3 seconds, which, given that my question only has 2 significant figures in it anywhere, I'm going to make 2 significant figures. I'm going to call it 110 seconds. So just under 2 minutes. I'm thinking, 2 minutes to get from -20 to 80? But it's only 80 grams of ice. 80 grams of ice is, less than your dad perhaps has in his gin and tonic. And a 500 watt immersion heater, that's a immersion heater. That's 3 of them would be the heater you have in the hot water tank. So perhaps 2 minutes is reasonable. Perhaps I should have made that slightly smaller value, and then it would have been a longer time. And again, you've probably watched the video of me doing this immersion heater. Nothing like a 500 watt immersion heater, more like a 20 watt immersion heater. And I had something like 80 grams of ice, and you all watched me stir it and 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 stir it, and it just stayed at 0 degrees C, because it takes a lot of energy to convert ice into water. 330,000 joules for every kilogram. Okay, that's it. That's me fly through the topics that I'm going to put in the exam. So those topics were using kinetic energy and GPE to do calculations with. The particle. Brain stop. The particle model of matter. How that particle model explains pressure in gases and the formula for pressure in gases, Boyle's law. and then going on to how that particle model explains what's happening when we heat and cool substances. And so when we're just heating it or cooling it, that's our equation, MCAT. But when we get a change in state, that's our equation. This is the latent heat, the specific latent heat, the energy necessary to cause that change in state. And when this is occurring, we don't get a temperature change because it's the potential energy part of internal energy that's changing. It's not the thermal part of the internal energy that's changing. Okay, I hope that made sense. If there's bits of that don't make sense, then go back and find one of those videos on that list of videos that I gave you to perhaps go over that bit again, or find another video on YouTube. There are hundreds of physics teachers who put videos on YouTube. Find somebody else's video and just double check that any of these bits that I've flown through here that you don't understand. Please do the exam. I know that some of you are not doing everything we set. Please do the exam, because I need to know what you have or haven't learned over this period. Please take it seriously. You're obviously in a position to be able to cheat. Please do the exam. If you end up with a really bad mark, that just tells me that later on in the course I'm going to have put some time into going back over this stuff. I need to know how much of this you've taken on board whilst you've been working by yourselves. It hasn't been easy working by yourself. So if you haven't taken on board lots of this, we won't be pointing fingers and going, this guy's incompetent. Well, we might be, but we shouldn't be. But I do want to know how much you know, so that we can get on with the rest of the school year. Especially now, there's a chance of us getting a couple of lessons in where you started to come back. I don't think we'll be doing anything like lessons for the first couple of weeks, but hopefully, once everything settles down, we'll actually be able to get on with some lessons. Okay, thank you for listening. Good luck in the exam.